All right, so it's 3 o'clock and it's time to start this webinar. So, good afternoon, everyone, and a very, very warm welcome to today's webinar, which is on chasing contamination, geophysical frontiers in environmental cleanup. I am Dr. Sanjay Rana, and I'm delighted to see participants joining us from across different sectors. We have registrations for more than 67 countries, and that's very interesting. Not everyone has joined the webinar till now, so many of them actually like to enjoy the recording later. So, but whether you're engineer, researcher, policymaker, consultant, or a student, I'm sure this webinar has something for you because we will explore how geophysics is playing a critical role in identifying and managing subsurface contamination across landfills, industrial sites, and groundwater systems. From mapping hidden pollution plumes to guiding remediation planning, geophysical methods are becoming indispensable in environmental cleanup today. So, over the next hour, I'll be sharing both the science and some practical case studies that highlight how these techniques are transforming the way we approach contaminated sites. I'm also joined by Dr. Paras Ranjan Pujari, a research scientist in CSIR NERI, who will also be sharing his expertise in this webinar. And simple housekeeping rule that is, please write down your questions, whatever comes to your mind during the webinar, and you can also post it in the chat. But we will take all the questions at the end of the webinar. And before I start, I would like to thank the entire team behind this entire webinar series, starting with Mr. Rashik Kathuria. He's the main person who takes care of the complete IT and the platform and all the Zoom links you get. So big thanks to him for all the efforts. Ms. Pragya Sharma, Secretary General of Aqua Foundation and AF Academy, integral part of the team and the brain behind whatever is done in Aqua Foundation. Ms. Anushka Batra, again, one of the most energetic and enthusiastic team member. Today we have the youngest one also. You get all the mails from her, reminding you all the social media posts. Shows she is the brain behind so much of work which is being done for these webinars and the entire INSG. Ms. Suchetna Banerjee, senior geoscientist, alumna of IIT Kharagpur, and again, helping a lot in the entire functions of INSG. Ms. Priya Mohini, geophysicist, to the best of my knowledge, the first geophysicist to come from the state of J&K. And again, she is very active on social media and keeps reminding all of you on the dates and times of these events. So, thanks to all of them, my acknowledgement to all of these people. And with this, let me begin by sharing my screen and walking you through my presentation, after which Dr. Pujari will take over, and that's how we'll conduct this webinar. So I'll start sharing my screen now. And like always, a quick check with Rashik ji. Everything is good. Screen is visible.
Yes, sir, it's visible.
All right. So this is third webinar in the series of our free pre-conference webinar series leading to Indian Near Surface Geophysics Conference, which is happening from November 12th to 14th in New Delhi. And this is on chasing contamination, geophysical frontiers in environmental cleanup. We have already conducted two webinars. One was on dam safety. The second was on urban geophysics. This is the third one. And the next one is on AI, ML, drones, and integrated geophysics for subsurface challenges. I'm sure it's going to be another interesting webinar. It's on October 4th. And then the fifth and the last webinar will be on powering the energy transition, where we are going to look at geophysical techniques in pump storage, solar, wind, siting, etc., which will be on October 18th. So if you're not registered already for these webinars, please go to this link, nearsurfacegeophysics.in webinars, or you can also, uh, you know, uh, scan this QR code which is coming on your screen and do it. And before I go any further, I'll just share my screen again. Yeah, all right. Okay. So Now, I'm a geophysicist by profession. I represent Parson. I'm also chairman of AF Academy, and Parson is the geophysical company which I represent, which is a ISO certified company. We are the largest in near surface geophysics in the country. More than that, we are very proud of the fact that we have been bringing various latest technologies from time to time, starting from GPR in 1996, the first GPR application in private sector, to shave a fraction to high resolution tomography. And anyway, I'm not going to go through the list, but this is what we are very proud of, that whatever is the best available in the world, we try to bring it to India. Our main strength is our people who are highly experienced and trained. We are an Indian multinational, so we have offices in India, in Bahrain, in Saudi Arabia, and in Singapore. And we are working in 14 countries around the world. Brief introduction about myself. I'm a geophysicist by profession, as I said. I'm working in this field for last 35 years now. Graduated in 1990 from University of Roorkee, which is now IIT Roorkee. And initial 5 years I spent with the state government and then the central government. And then 1995 is the time when I founded the first private company in the field of near surface geophysics. And since then, I'm just doing that. And it's very important to have good standards, good codes for all the services. So I'm a member of various committees for development of codes and codes of practices and standards, including Bureau of Indian Standards, BIS, Indian Road Congress, TAI, INDCT, etc., etc. So this is a brief introduction. I think that's good enough for the starting. So now coming to geophysical investigations. So before we go into the topic of contamination or contaminated sites or environment geophysics, I would also like to just give a very brief about geophysical investigations for uninitiated, because there are many participants who come from engineering background or geology background or science background who are not exactly from geophysics background. So it's very important to explain geophysics in just 1 or 2 slides, so that after this webinar you can go back home and explain this to your 5-year-old also. I'll keep it as simple as that. So when I explain geophysics, I love to start with comparing it with medical imaging. So the what you see here are medical imaging pictures. Of course, you have ultrasound, you have X-ray, you have CT scan, you have MRI, etc. And what we are doing here is that we are sending different kind of rays and waves inside the human body to create an image of what's inside the human body. That's exactly what we are trying to do here. And if you compare this with geophysical images, so what you have here on screen now are geophysical images. So this, for example, is a shear zone in a otherwise rock. These are reinforcement bars in a concrete slab. These are pipes buried under different layers of road. This is a hydropower site, so the rock interface, etc., etc. So in geophysics, we are practically doing the same thing with a medical imaging professional is doing on the human body. We are doing the same thing on Earth. That is, we are sending different kind of rays and waves inside the Earth or across the structures to create an image of what's inside the Earth. And we are not only sending rays and waves, sometimes we are also measuring naturally occurring fields like magnetic field, like gravitational field, like telluric field, etc. Idea is to create an image of what's inside the Earth. So this is the simplest way to understand what we are doing in geophysics. Okay, so it is like doing X-ray ultrasound of Earth. That's what we are doing. Just like in X-ray ultrasound and medical imaging, you have number of techniques. Similarly, in geophysics, also we have number of techniques. Depending on what is the problem we are trying to address, which physical property is going to give the maximum contrast, we are choosing the particular technique to be used. And then why it is so important to use geophysics practically for any project which you are doing on the surface of the earth. The answer again comes from the comparison to medical imaging. Why it is so important to do X-ray ultrasound before you carry out an operation or a surgery? Because it is rapid and cost effective. So today, for example, using heliborne or airborne geophysics, you can cover hundreds and thousands of kilometers in a single day. So it's very quick, it is cost effective. Just like X-ray is more cost effective than a surgery. Surgery should be done only when the investigation has been done properly, right? Non-destructive. So, unlike doing any other test like drilling or trenching or pitting, it's totally non-destructive. That is, it does not leave any mark on the ground once you finish a geophysical investigation. And most important, continuous information. Whatever traditional methods we are using, we are getting discrete, accurate information, but only at that particular point where drilling has been conducted. For example, you take look at this diagram. You have a void here, a limestone pinnacle, different anthropological features, and you are doing drilling. What are the chances of detecting all these objects by drilling alone? Chances are 1 in 1,000 or 1 in million, depending on the spacing between your drill holes and size of these objects. Whereas, if you do a good geophysical campaign, you can map all these objects and then optimization of drill holes. That is, target your drilling only where you see the anomaly or you really want more information of that particular zone. So that's where the strength of geophysics comes from. It doesn't live in isolation. Never take a message home that geophysics replaces drilling. It does not. It optimizes drilling. It makes the entire process more scientific, faster, more reliable, and it cuts on surprises. Whenever we are conducting a subsurface project, whenever we come across a situation which we did not anticipate, like a shear zone during tunneling, we call it we met with a geological surprise. Well, it's not a geological surprise, it's a situation which you did not anticipate because you did not investigate. All right. Discrete point investigation can never give you holistic information about the subsurface, right? So geophysics leads to minimization of surprises, and of course, it is good for early stage application. Just like X-ray, ultrasound should be done before the surgery, so you know where exactly is the problem, and then you can even do laparoscopic surgery with minimum invasion to just reach that problem and treat that. Similarly, if you do a early stage geophysics, you can target your drill holes and ultimately optimize the entire process. Unfortunately, despite me talking about it for last 30 years, still 90% of the calls which we get are firefighting calls. That is something which needs to be changed. That is something these kind of awareness programs which we do through these webinars, etc., come in picture. That this should be done in the planning stage, the early stage.
Greetings.
And
We
if
are
you
very
want,
excited
of
to
course,
share that the
if you are
third
excited about geophysics, this is the third Indian Near Surface Geophysics Conference and Exhibition, which is happening from 12th to 14th November. And I welcome all of you to be part of it. This is just a 45 seconds video, just introducing this conference to you.
Indian Near Surface Geophysics Conference and Exhibition is coming up this November. It is being organized by ACO Foundation Academy in collaboration with EAG. The event will take place from 12th to 14th November 2025 at the Surya in New Delhi. This year's themes touch on some of the most critical areas from engineering and environmental geophysics to urban mapping and energy transition solutions. From seismic refraction to ground penetrating radar, this conference brings it all under one roof. Two pre conferences are also being organized on 12th November 2025, focused on dam safety and contaminated sites. We will also be presenting the most awaited INSG Awards and Dam Safety Awards for this year. So, if you're working in geoscience, infrastructure, environment, or research, this is where you'll want to be. Please visit our website and register now.
All right. So now coming to the topic of the day. So first of all, why environmental cleanup needs new frontiers? What this topic is all about. So let's try to understand it this bit. So environment contamination today is a growing crisis. Industrialization, mining, unregulated waste disposal have led to widespread subsurface pollution. We very well know about it, how things are happening, what kind of problems we are having in terms of contamination. The pollutants which are there ultimately infiltrate soil, groundwater, and landfills, and often going undetected until damage is extensive. We are not having a mechanism for a very regular check of how these contaminants are actually infiltrating through our soil and contaminating even the groundwater. We have conventional methods like boreholes or chemical sampling, etc. But as I said, they are limited, invasive, and discontinuous. That is, you are only getting point information in all these cases, right? So this is where we are having the challenge. The challenge is first to find out where is the contamination. How far has it spread? You have got a landfill here. Now, this landfill might have led to some contamination, but what is the spread of this contamination? Okay. What lies buried beneath? That is trying to have an eyes to see what is underground, what is beneath. And this leads to opportunity for non-invasive, real-time, and scalable solutions to detect and map contamination early. When we say early, at a stage when already they are not doing irreversible damages, right? So detect and map contamination early, support cleanup and rehabilitation, and monitor remediation effectiveness. You are doing cleanup, how to plan for it. You're planning a rehabilitation, what's the best way to plan for it? You are doing remediation of a site, how to monitor the effectiveness of what you are doing. It's just you cannot just assume that we did what was given in our scope of work and the site has been remediated. That's not how it works. You need a tool to understand what is the effectiveness of the whole thing. So that's where the role of geophysics comes in environmental cleanup. So why, first of all, why? As I said, traditional investigation like boreholes, test pits, sampling, etc., are localized, invasive, and often miss hidden contamination, right? So that's the first thing. They are not continuous, they are local. Environment contamination is three-dimensional and actually it's dynamic. So you can add the fourth dimension also, and that's time. So it's not just three-dimensional, it's three-dimensional and dynamic. So it requires continuous non-intrusive exploration method, and that's where geophysics fits in. Because geophysics gives you imaging of the subsurface without excavation. You don't need to take out your soil or excavate, etc. It can detect your anomalies, fluid movement, buried waste, buried drums, etc., etc. It's real time and wide area coverage, so you can cover a large area with high resolution. So in cleanup projects, when we talk about map pollution plumes in groundwater and Vedos zone, detect buried waste, leachate tanks and liners, guide remediation planning, that is location of barrier walls, wells, monitor effectiveness of ongoing or completed remediation. So these are the pointers which where geophysics fits in. It just does not locate the problem, but it also helps solve the problem in a non-invasive manner. The key geophysical techniques which we are using for environmental purposes are: first is electrical resistivity imaging, of course. It maps leachate plumes, detects moisture, salinity, anomalies, etc. Ground penetrating radar, which is great for locating buried waste, tanks, trenches, interfaces. MASW, which is used for assessing the soil stiffness, detects voids, differential compaction. Even when you are doing remediation to see the stiffness at different levels, MASW is a great tool. There are other methods also, like EM surveys, induced polarization, seismic refraction, time lapse ERT, as I said, adding the dimension, fourth dimension. For example, you want to see how a particular plume is moving with time. That's where time lapse ERT comes, that you are repeating the same survey over a period of time. So this you can see is a toolbox. And I'm not challenging any one of you if you can just add three more methods into it, because there are total around 19 methods which can be used for environmental geophysics. For this webinar, definitely we are picking up the one which are most effective, right? There are other methods also, no challenge on that, but I'll be presenting mostly on these methods. So first we'll start with GPR, that is ground penetrating radar. Ground penetrating radar, as the name itself suggests, radar. There is a word radar in that, right? We all have seen radars in our life. If you go to airport, you see this whole thing which keeps rotating, and that's a radar. Radar was basically invented in the wartime to detect enemy ships and enemy's aircrafts. And today also this is something which is used to detect in the free space for our aircrafts and things like this. It's obviously for it radio detection and ranging. That's where radar comes from. So what we are sending here, what we are doing here is the transmitter receiver. We are sending radio waves. They are going in the space, getting reflected wherever there is a change in the dielectric properties, because they are electromagnetic waves, so the change has to be in dielectric property. Wherever there is a change in dielectric property, reflection takes place, and again they are picked up by the receiver. Transmitter is sending, receiver is receiving. So this is radio detection, that is detecting using radio waves. Next is ranging. Ranging is measuring the distance. So if we know the velocity and we know the travel time, we can measure the distance, right? So that's how we are doing radio detection and ranging, and that's radar. Same radar, when we are putting into the ground, it becomes ground penetrating radar. It is also called geo radar. It's called in short form GPR. It is called subsurface interface radar. There are many names for this, but ultimately the basic principle remain the same. You have a transmitter, you have a receiver. Transmitter is sending electromagnetic waves. Now this time, instead of sending in the space, it is sending in the ground. So it's become ground penetrating. So you're sending electromagnetic waves inside the ground. They are hitting any interface across which there is a change in the dielectric property. In this particular case, for most of the calculations, we take a property called RDP, relative dielectric permittivity. We also call it dielectric constant. RDP is more well known, so to say, because it's relative to the air. So RDP, wherever there is change in dielectric property, the reflection will take place and now picked up by the receiver. So it is working in brief on the principle of electromagnetic reflection, right? Electromagnetic waves being sent, getting reflected from various interfaces across which there is a change in dielectric property. Now that makes it very interesting. It will pick up different soil interfaces because there'll be change in dielectric property. It will pick up buried pipes. It will pick up buried drums, USTs, anything which is different, right? It's great and it's troublesome also because it just picks up too many things, and that makes sometimes very challenging to interpret the data of GPR, but not going in that part. So it shows very beautifully the working principle. So here is the antenna. It is a combination of receiver transmitter. You can have receiver transmitters separate also, but most of the users are having one box which has receiver and transmitter. So one pulse will look like this, which it goes down, comes back. So wherever it comes back, you will see. So this will be time. This will be amplitude. More the contrast, higher the amplitude. So this will be called the A scan. You put number of the A scans together because it is sending hundreds of these pulses per second. So you put all of them together, it becomes a B scan. This is what you see on your screen in real time. Then you take number of these B scans and process this data together. It marks almost a three-dimensional part of it. It becomes a C scan. So this is a very, very short working principle of GPR. So it can be used for understanding the stratigraphy of a site. So here, for example, you can see this is time in nanosecond. This is the scale in depth, and this is one horizon. This is the another horizon. This is the another horizon, and this is the basement. Okay, so like this, you are able to see stratigraphy of the site using GPR. You can detect underground storage tanks. So these are the detection of underground storage tanks. In fact, it's very interesting, and many of you are obviously joining from outside the country also. In many countries, uh, pollution is belongs to you. So if you buy a property and there is a contamination source under your property, once you have bought it over, now it belongs to you. So it is almost mandatory that when people are buying property, they get this kind of a survey done to detect if there is a buried storage tank or there is anything buried in the property so that they do not become liable for what they did not do at a later date. All right. So this is a good example of how it detects tanks. Here is an example of how it shows the pipes, underground pipes. So it's an excellent method to detect subsurface interfaces or objects in very high resolution. When it comes to pollution, it can directly sometimes give you the information. So this is the example where these are the buried drums. So these are all buried drums. And here this is a zone of attenuation of signal, which is due to hydrocarbon contamination. This again is a zone of contamination because of hydrocarbon contamination. So sometimes you are able to detect directly the anomalies in the subsurface, which is happening because of contamination. We did a major project in Madagascar long time back, so must have been around 18 20 years back now, where there was a lot of oil spill in a particular area, and they wanted to understand what is the depth of contamination because of this spill, because site was changing hands, the owner was changing, and he wanted to assess how much removal will be required for remediation. And for that he wanted, so we did extensive GPR in that site to understand that. This is another example, very good example of direct detection mapping of plume. So this is a profile where this is a plume which is named as FT02. So this plume has been detected because of amplitude shadow. Now, what is amplitude shadow is that if a particular zone becomes more conductive, the EM waves will be absorbed in this more conductive zone. All right. And you will not see much reflection coming from this zone. And that will create an amplitude shadow. So this is the example of an amplitude shadow which is being created because of a plume. Another very beautiful example. Here you can see this total 400 nanosecond, and this is depth in feet, around 40 feet here. This is the water table, which you see. And under water table, here is the amplitude shadow. So this amplitude shadow basically shows a more conductivity in this particular zone. That is concentration of contamination in this particular zone. Same example here, another example, water table here, and this is the amplitude shadow. So these are examples of direct mapping of plume, which you can do with GPR. Now, once we talk of GPR and we show you these great examples, it comes to mind, oh wow, then this is the technique. Why do we need anything else? Couple of things. First of all, GPR does not give you material properties. It only gives you interfaces or absence of interfaces which are being created because of higher conductivity, right? It will not tell you what the material is. That's one, because it is only working on the principle of EM reflection. And two, and very important, GPR performance is extremely dependent on the site condition. In a very dry condition, GPR can be a great tool to go to tens and sometimes hundreds of meters. I'm saying it with a lot of responsibility. Entire ice thickness mapping of Antarctica has been done using GPR, which goes into kilometers. So depending on material property, the depth of penetration varies. Otherwise, it is in tens of meters only. Let's not, go beyond that. But in very conductive soil, it can remain in centimeters. All right, you might not have any penetration altogether if the soil is very conductive. So GPR is extremely dependent on the soil properties, and of course other limitations which comes based on the working environment. So coming to the next method, GPR is great method, high resolution in the right soil condition. It will not tell you what the material is, it will tell you interfaces only. So coming to the next very important method, that's electrical resistivity imaging, one of the strongest method when it comes to environmental geophysics. In which what we are doing is we are putting these multiple electrodes on the basic principles remain the same Ohm's law which we studied in our 8th standard hasn't changed at all right. So we have voltage, we have current, we can measure resistance, and same resistivity method which was the first geophysical method to be used for oil and gas exploration long back. Only thing that has changed is microprocessors have come, computers have come, so things have become a little different. So now we are putting number of electrodes together. For example, we have got 120 electrode system also, and it is connected to a switcher and a computer. And combination of electrodes are now being switched by the switcher automatically. So you get resistivity at different depths as you go from one end to the other. So at the end of it, you can create a 2D or a 3D image of the subsurface in terms of resistivity or the reciprocal conductivity, right? So whenever there are changes in the subsurface, which are changing the resistivity or conductivity, you are able to map these beautifully using electrical resistivity imaging. And when pollutants are entering the ground, when contamination is entering the ground or moving through the ground, it is changing this very property a lot. And that is what makes electrical resistivity imaging such a strong tool. So once you put your electrode, do all the measurement, which generally take 20 to 30 minutes to take for a line length of, if it is 60 electrodes, 5 meter spacing, 300 meters of line, 20-30 minutes, and you're over with this. And then it gives you a 2D image of the subsurface in terms of resistivity. So if, for example, rock here, so very high resistivity, tree roots here, low resistivity, etc., etc. Once you have, for example, this is a good example from Loke's notes. He has done the maximum work on the inversion of the data. He is the founder of 2D REST 2D in software. So, for example, you have boulders. Boulders mean high resistivity. You have zone of water accumulation, which will be low resistivity. So, beautiful 2D. This is the depth. This is the distance. So, 2D or 3D information of the subsurface. Here, example from environmental point. So this is the leachate plume, contaminated groundwater. So groundwater is contaminated, means the resistivity will go much, much low. More contamination means more ions for the flow of electrical current, which will basically lower the resistivity, that is increase the conductivity. And I'll take you to a very beautiful case study on this, which is by one of my friend, Mr. P.K. Maurya from Aarhus University. And this is on detailed landfill leachate plume mapping using 2D and 3D electrical resistivity tomography with correlation to ionic strength measured in screens. So those who are interested in more details of this, I will share it after this lecture. You can just send a message to me and I'll share this case study also. But I'll just try to show you the main points of the case study. So this is a site. Here you can see this is strong leachate, then medium, and then weak. Here are the 3D ERI lines which were done. These are 2D lines which have been done, profile 1, profile 2, and profile 3. And of course, there are these shallow wells. These are all shallow wells and they are deep wells from where the ionic strength has been taken. So this has, first of all, both the 2D and 3D has been done to understand the spread of this plume and also to correlate with the ionic strength. And that's what makes it a very good case study. So this is the first profile. So this is the profile 1. This one is the profile 1 here. You can see it has been done here. And you can see this particular low resistivity zone. This is the extent of the plume. As you can see here, it is lowest resistivity, which is showing the highest ionic strength here, which also correlates with the observation because this bar is showing the ionic strength, lowest resistivity. And as it is going away in this direction, resistivity is gradually increasing. Okay, this is basically a depth of investigation. And this correlates so beautifully with the ionic strength and shows the entire strength of the plume as you are going in the direction of the flow. This is line 2 and line 3 combined. Same thing, it has been done. As you can see, line 2 has been done here, line 3 has been done here. Both have been combined in this. And again, you can see the entire extent of the plume in this. This is the plume. And ionic strength is correlating very well with the resistivity which has been detected at these zones. And this correlation makes it a very beautiful case study to talk about. Then the 3D lines have been done, 3D inversion has been done, and at different depth if you are seeing. So this is minus 30 meters, this is minus 20 meters, minus 10 meters. So at this particular depth, entire thing is concentrated. This is a landfill. In the dotted stars, you see the landfill. Everything is concentrated close to the landfill. As you go further away, now it is moving in the deeper layers, it is moving away from the landfill. And again, as you go further deeper, it is moving away from the landfill. So you can see the entire movement of the contamination, the plume, in the direction of the groundwater as you're moving away from the landfill. That same thing has been done in the 3D. So this is a 3D cube. This is the landfill. And this is the hotspot plume, which is coming from industrial waste. So this is having a much lower resistivity than the waste plume, which is coming from the hot household waste. So you can see again how this is the ground approximate flow direction. And you can Again, this particular cube you can cut at different places to see how the contamination is moving from one end to the other. So this is how you electrical resistivity imaging done in 2D or 3D can give you a very beautiful holistic picture of your entire site. What is the extent of the contamination, in which direction it is moving, etc., etc. The best part is that if whatever data you are having from your sampling study or borehole study, you can use that data to train this model. That is what resistivity is correlating with what kind of ionic strength. And that way you can extend your point data and accurate point data to the entire area. That is the strength of combining the whole thing. Then there are cases when you can look at your stratigraphy. Sometimes you want to see fracture in your bedrock. So this is one good example where you are seeing this is one interface. All right. So this the top of transition layer. Then the second one is the top of clay horizon. Then you have top of the bedrock. And here you are able to see the fractures in the bedrock, which are so important when you are looking for doing any planning in your landfill or contamination. This is a case study which for a project which we did, which is a very interesting case study. So I thought I'll present it here. So this was a mining area. So filling of slime was done here. And then at one point, a sinkhole got created, and about 60,000 to 70,000 cubic meter of this slime went underground. Okay, there was no oozing being seen from anywhere. So the next thing was where this entire slime has gone. Right. So geophysical investigations, hydrogeological studies, we did induced polarization, ERT in this particular area to understand what's happening in this area. And this video basically shows how the this sinkhole which was developed, and now entire slime anyway has gone. Whatever is remnant, then only the photography was done to see where it is going. So this is how the ERT lines were planned in the entire area. Number of lines wherever it was possible were done. And once we did this ERT, we were able to see beautifully these zones. These are the low resistivity zones, as you can see in the subsurface. You can see these zones. This is all secondary porosity. All right. This area is rocky area. Entire thing was secondary porosity and filled with slime. This was completely conductive. So it was having low resistivity. And see all these places, all these low resistivity zones which were mapped, and after that, all these zones were marked on the map to understand where this entire network, how this network is interconnected. This also was plotted in 3D. So as you can see, this was not 3D exactly, in a perspective. So you can see all these zones, and from this you are able to make out how the zones are interconnected in different directions. You can see the interconnection of the zones. So these reveals the presence of fraction network, that is secondary porosity in the subsurface, which becomes basically conduit for the slime. Based on these results, various weak and saturated zones were interpreted in and around the slime dam, which were then marked in various sections. There was a very good correlation of the geophysical anomalies and geological features, and many ERT profiles showed these zones. Based on that, it was inferred how the slime has moved once it has gone inside. So as reported, the chemical composition of slurry contains higher concentration of Fe, Ai, Mn, heavy metals, and of course, leakage of such slime in ground or in contact or contact of the water may result in contamination because these metals may dissolve. So it was very, very important to understand where this slime is going and what is the behavior. As I said, you can do 2D, you can do 3D. So this is one example of 3D imaging where it is not exactly 3D again, it's 2.5D because it has been done using number of lines in longitudinal and cross direction, not by 3D electrode arrangement. This is all water table which you see, this blue one at the bottom. And as we cut the slice from one end to the other, we'll be able to see this is the extent of a anomaly, which was basically a cavity. This blue one which you see going from one end to the other. So this blue one is the anomaly. As we go down, you'll be able to see across the profile like this. Okay. So you can actually do ERI in 2D or 2.5D like this case, or real 3D like earlier case, to understand your site in a wonderful manner, absolute completely and holistically. Next method, which also is applicable, is seismic refraction tomography. As I said, in electrical resistivity imaging, we are measuring the resistivity. Sometimes we want to measure various layers in the subsurface based on strength. Strength, compressive strength is P wave velocity. So seismic refraction tomography gives you P wave velocity, and it is working on the principle of refraction. We are starting, acoustic energy on the surface by using hammer, explosive, weight drop, whatever it is traveling inside. Refracted waves are being received by geophone, and ultimately we are getting a subsurface image like this. So you have topsoil, you have this interface which is between topsoil and the weathered rock, and then this weathered rock and hard rock, and you can see the complete topography. It's not like drilling. For example, you just do one drilling here, you will think that this soil is going like this, whereas the soil thickness is completely varying throughout the profile. It's very fast, it's very cost effective, and it's very comprehensive. Even small features like fractures, small fractures you can detect in the rock, which is very important when we are doing when we are studying the suitability of sites for landfill or remediation, etc. You can interpret the entire data into translate into geo model. So for example, the topsoil, highly weathered, moderately weathered, fresh to slightly weathered, etc. And this is one very good example, because sometimes we want to understand clay is the layer which is impermeable layer, all right. So that gives us practically uh, a barrier for transportation of pollutant. And sometime in a particular site we want to see how the thickness is varying in the entire area. So this study shows very nicely the thickness of clay, and these red are the areas where the clay thickness is 5 feet or less. So you have studied the entire area very quickly, and now you can zero down on the area where thickness is less than a particular threshold. So you know that these areas will need further treatment or will need further effort before the site can be used for any particular purpose. Magnetic survey again is an important tool which can be done, because they are used for mapping landfill boundaries due to high metal content of municipal waste. If you're using municipal waste and metal content is high, you can use magnetic data for that. So this is a magnetic survey. You can see this area is having very, very high magnetic concentration. MASW, just like seismic refraction gave you P wave velocity, sometimes we are interested in shear wave velocity, and MASW can be used for that. It is working on Rayleigh wave dispersion curve, and with this you can find your shear wave velocity of various layers. Last method in the arsenal, I think I'm going to talk about the cross-hole tomography. Sometime you want very detailed understanding of a particular site in terms of underground cavities, fracture zone, fracture network. So there, between the drill holes, which you're already doing for any purpose, if you just conduct tomography between these holes, now you just do not have discrete information, but continuous information between your holes. So this is a very good example. We are very proud of this case study. This is the deepest seismic tomography reported in the world till date. Our boreholes were 250 meters deep. Distance between borehole at one point was more than 115 meters. And this is a signature of cavity which was detected using this. At one time, cavity was as big as 85 meters by 60 meters. So these are the methods I quickly wanted to talk about. And it's very important to integrate geophysics with your remediation planning, because environmental geophysics does not operate in isolation. Its true value emerges when integrated with environmental engineering, remediation, and risk assessment workflow. So, how geophysics supports the entire project? First of all, define the extent of contamination. Identify lateral and vertical boundaries of plumes, waste zones, impacted soil, etc. Optimize your remediation design, that is support placement of extraction or injection wells. Once you understand your subsurface better, you can plan your wells better. Barrier walls or phytoremediation zones with accurate subsurface data. Reduce risk and cost. Minimize over engineering or under engineering, as we say, by targeting actual impact zone. Monitor remediation progress, that is repeat surveys. time lapse ERI or GPR. So you have done the survey today, you do it after 15 days, after 1 week, after 1 week, you can see how your remediation is improving the site. Okay, you can track the changes of subsurface conditions over time. You can do it after 1 year also. And then the beautiful examples or beautiful ways to integrate geophysics, that is, you have resistivity map overlay with chemical sampling data or hydrogeological model, like the case study which I had shown. Resistivity with ionic strength, put them together, you get much more value out of your data. Use geophysical inputs in numerical transport model to simulate pollutant migration. Combine with risk assessment tools to prioritize cleanup action. So this is how you integrate geophysics. So geophysics doesn't just help find contamination, it also guides how we fix it. That is the basic message. So it is basically a game changer because rapid and wide area coverage, non-invasive minimal disturbances, cost effective compared to dense drilling, use for pre-investigation, monitoring and post-remediation verification. There are of course challenges, that is site can be extremely heterogeneous or there might be anthropological noises. It needs calibration with some lab data or borehole data. Interpretation expertise is critical. Unfortunately, with extensive uses of software, uh, people have a tendency of just putting data and taking some colored map out. Without expertise, you cannot really do a good job there. Regulatory acceptance is growing but is still evolving. That's a big problem. So those of you who come from regulatory bodies or policies or government departments, try to make geophysics as part of your campaign when it comes to contaminated sites. Future direction will be 4D, time-lapse geophysical monitoring, drone-enabled surveys, integration with artificial intelligence, machine learning for anomaly detection, real-time sensors for dynamic site monitoring. These are the future directions. There's so much to talk about, and this time is just too limited. So if you want to learn more about it, we have put together this wonderful training workshop, which is happening on November 12th uh, in Delhi, which is on geophysics for subsurface characterization of contaminated sites. The workshop is being conducted by a few of the best names in the field. Engineer N.K. Verma is a distinguished professional with a very long background working with the contaminated. He also had a background of CPCB. Professor Ilango, visiting faculty IIT Madras, again having extensive 38 years of experience. Dr. Parasanjan Pujari from NIRI, chief scientist. I'll be anyway introducing him shortly, a bigger introduction. So these three gentlemen are going to take this workshop on November 12th. So those of you who are really serious about it, spend a day with them and learn more about it. You can register this very quickly by just scanning this QR code. Otherwise, team will put this registration information in the chat also, and you can do there. Now I will be coming to the next speaker of the webinar, Dr. Paras Ranjan Pujari. As I said, he has 25 years of professional experience as a research scientist in CSIR NIRI under the Ministry of Science and Technology, Government of India. At present, he is chief scientist and head of the Water Resources Division. He has played a significant role in developing the environmental geophysics area in the country. He has contributed significantly to the use of geophysical tools in contaminated site characterization, structural integrity of secured landfill sites, managed aquifer recharge studies, seawater intrusion, monitoring in situ bioremediation, etc. His efforts have led to development of long-term monitoring of critical zone processes of the Narkhed Pandurana Critical Zone Observatory in central India. His research work has led to impact on society, industries, and regulators. His dedication and passion has led to Institute being a pioneer in the field of environmental geophysics and hydrogeological studies. As expert member of regulatory board, that is Gujarat Pollution Control Board, and different NGT committees, he has facilitated policy decisions in groundwater management and remediation, fly ash management by coal-based power plants. With this, I hand it over to Dr. Paras Ranjan Pujari, and I'm sure you would love hearing from him on this topic further. Dr. Pujari, over to you.
Yes, thank you, Dr. Rana. this pre-conference webinars. And first of all, I must thank Dr. Rana and his team for this opportunity. And thank Dr. Rana that he's one person professional who really loves to work. And he has been at the forefront of taking near surface geophysics to new heights. And it's good that we have as many as 100 participants. And already by some introduction has been given by Dr. Rana. And yes, in fact, when Dr. Rana graduated and I graduated way back in the early 90s, geophysics was all about basically using it for this oil exploration, mineral exploration, or to some extent or to a large extent in groundwater exploration, but its application in engineering and environment was limited. And but now we have come a long way. And I'll describe about my experiences of working in NERI and where I felt that as geophysicists, we have a lot more role to play when working for the society, for the nation. So next, yeah. Now, if you look at this miniature of our Earth system, right from this top of the tree canopy to then you have this soil followed by the fractured medium, then hard rocks where you have this groundwater occurrence. This entire zone right from the top of the tree canopy to this bottom of the aquifer, this is something that we call critical zone. And you call it critical because it is critical for our survival. Everything that you need, be it water, food, then the fiber, then agricultural products, everything depends on this particular zone. And this is what we call critical zone. It's extremely important for our livelihood because it gives you all the ecosystem services. But over the last, say, so many years, so many decades, right from our industrial revolution, then we have this critical zone under tremendous stress because of different anthropogenic activities. Anthropogenic activities, mainly these industries, because that's a big part of our economic activity. And from industries, we have significant generation of industrial waste, both solid as well as liquid waste. And if they're not disposed properly, ultimately they get into our soil and groundwater medium and contaminated. Same thing is with our agriculture. That's also a big part of our economic activity, and application of fertilizers can ultimately have adverse impact on the soil and groundwater. Then we have other things like growing urbanization, that leads to significant generation of domestic waste, and everywhere you have big unsecured landfill or solid waste dumping ground, and that becomes a big source of pollution for the groundwater and the soil medium. Next. Yes. So what are the major sources of groundwater and soil contaminants? So basically, these are all application of fertilizers. Then we have this seepage from septic tanks, because not all the cities are having 100% centralized sewerage coverage. And we have a lot of septic tanks. And very recently also, you have seen that following the Swachh Bharat mission of the government of India, when septic tanks were constructed all over the countries, but at many places, they're not constructed of scientific lines. And if there is not good engineering, there can be seepage from septic tanks, and especially in hard rock areas, which cover as many as 60% of the country, there is a potential contamination of groundwater from these septic tanks. Same thing is with domestic waste dump site and landfill, and seepage from industrial waste disposal sites, and solar evaporation ponds which store this treated effluent from industries. And we can have this groundwater pollution from this petroleum storage tanks, the tailing ponds, and of course, large-scale groundwater withdrawal, especially in the coastal areas, ultimately lead to seawater intrusion. And we have a lot of salinity, all over the coastal areas, especially in Gujarat and Tamil Nadu. Next. So what are these major contaminants that we come across in groundwater? It is mostly nitrate, which is from application of fertilizers, the septic tanks, and the domestic waste dump sites. And sulfate, which comes mostly in places where there is gypsum sludge disposal, especially in industrial areas. Then higher salinity, it can be both geogenic as well as anthropogenic. And fluoride, it is mostly geogenic, and heavy metal, it can come from both geogenic as well as anthropogenic. And the bigger problem is most of the time the organic contaminants. And so, looking at all these contaminants, we need to somehow protect our environment, and environment protection is not just the job of the government or the regulators, but we all as a society have to protect our environment, because we have to, give a safe environment to our next generation. Next. Yeah. So, as I mentioned earlier, protecting the environment is the job of everybody. But if you look at this legal and policy framework, we had this Water Act, which was enacted in 1974. And that's when our regulator, Central Pollution Control Board, came into being. It was an outcome of this Water Act 1974, wherein it was the responsibility of the state to protect our water resources. And it is not just the Central Pollution Control Board which came into being, but it led to have state control boards being set up in different states. Then we had this Air Act in 1981, and that was followed by this Environmental Protection Act in 1986. And this Environmental Protection Act in 1986 was basically a game changer in India as far as the environment was concerned, because that time this Ministry of Environment and Forest also came into being as a very vibrant ministry. And under this Environmental Protection Act 1986, many notifications of environmental impact assessment and subsequent acts were promulgated. So it is this Environmental Protection Act which was a game changer. And then we had all these notifications. That was a follow-up to this Environmental Protection Act. Next. So as I mentioned earlier, so this environmental impact assessment notifications passed, it was in 1994 and followed by 2006. Then, of course, this draft notification has been there since 2020, and it is yet to be in the final form. So basically, these EIA notifications, environmental impact assessment notifications, are there for the industries. And when industries get this environmental clearance, there are environmental conditions also. What are these safeguards that they have to take for protection of the environment? So if there is not proper compliance, then we are bound to have some adverse impact due to their waste disposal management. And if you look at this municipal solid waste management, these rules are, fairly new. I think the first one was promulgated in 2000 and 2016. So you can see that there are these big solid waste disposal grounds all over these mega cities, and all these things have taken place because we did not have a proper mechanism, framework for proper disposal. And that was the PT. And then the most prominent source of pollution like this, that due to hazardous waste management, when it was there in 1989, followed by rules in 2008 and 2016, the initial regulations were very weak in many respects, because if there are hazardous substances and they are to be disposed of, then it was mostly, left in certain depressions filled with bricks. There is no mandatory double liner system. All these things were not there. And that led to, poor waste management by the industries. And very recently, we have this plastic waste management tools. But these things are there, the notifications are there, the acts are there, and we have still a new mechanism wherein people can go to the Honorable National Green Tribunal for any non-compliance, and we have a very strong judiciary also. So things are in place, and probably now it is getting more and more stringent, but it will take some time. Please, next. So as I mentioned, there is always some non-compliance of the existing acts, and this leads to unscientific practice in waste disposal and pollution of the soil and groundwater. And very often it leads to decades of litigation. Now, most of you might have heard about this groundwater contamination in Tamil Nadu that was due to this tanning process. People earlier used to, they use this salt for tanning process. And there has been a lot of groundwater contamination, especially in the tannery belt in Tamil Nadu. That was in the late 80s and 90s, and it led to big I think a big groundwater contamination problem, and ultimately it led to the Honorable Supreme Court ordering us, all the tanneries in the country, to stop the operations. Then Bhopal gas tragedy, we had it in 1984, but still there is a lot of hazardous waste lying, and there is always some dispute. Hatch acid contamination in Bichri in Rajasthan, and for your information, hatch acid is basically a dye intermediate. You all know about the dye being used in textile industries, which is a very big economic activity in our country, and India exports a lot of textiles. So hatch acid is a dye intermediate, and it is one of the most polluting industry. It is banned almost all over the world, except few countries which include China. And this hatch acid contamination has been reported in Bichri, then Ratlam in Madhya Pradesh. Very recently, we have come across in Punjab. Personally, I have been involved in that. And Padra in Gujarat, I am also personally involved in that. In fact, all these 4 cases have been handled by NERI in the past and at present also. Next. Basically, these are the landmark groundwater contamination cases in the country. That is why I wanted to share it with the participants. Now, this is this dumping ground at our mega cities, this Delhi, you can see Gazipur, and then Deonar in Mumbai, and dumping ground at Dhapa. This is in Kolkata. And it is observed that all these dumping grounds have led to elevated concentration of nitrate, downstream of these sites, and heavy metal contamination also. And it has led to a situation wherein this Honorable NGT has asked for restoration of the site. So restoration of the site means you have to first need to have detailed hydrogeological and geophysical study, and quantify the contaminated region, and then go for rehabilitation. This is where basically our hydrogeology, geology, geophysics, environmental engineers all have to work together. Next. Yeah, so this is about what I would like to describe about this classic groundwater contamination case in the Punjab state. And this is about an industry in the Sangru district. And this industry was started in 1991. That is when we did not have very robust hazardous waste management rules. And it is one of the highly polluting industry, and it is operational in very few countries, including India. And 1 ton of the dye intermediate, it generates 12 tons of mother liquor. You can just imagine. If you want to generate 1 ton of mother liquor, this H acid, that will generate 12 tons of mother liquor, and that is highly conductive. The TDS is something like 70 to 80,000 mg per liter. So you just imagine if a mother liquor of that tedious is if it is not disposed properly. I mean, then the potential groundwater contamination you can think of. And this industry was closed down in 2005. And after 4 or 5 years, I mean, people started getting colored water in many groundwater sources close to this industry. And the most disturbing part was this groundwater contaminated water was also it is still being used for agriculture. And because of these complaints about the contamination and subsequent action by the regulatory body, it has been declared as a contaminated site by the Central Pollution Control Board. And when it is declared as a contaminated site, then ultimately it has to be remediated. And for that, we need to quantify what is the extent of soil contamination, what is the extent of groundwater contamination, and then go for remediation. And this is where we got a sort of SOS from the Punjab government. And then, of course, it was a big sort of rescue mission through geophysical studies, because I mean, the entire area was abandoned more than 15 years back. The property was sold to somebody else, who in turn sold the property to some other person. And as Dr. Rana mentioned, that in Western countries, if you buy a property, you have to go for some kind of due diligence studies. It is not mandatory in our setup. And this property was lying abandoned. I mean, of course, it was the property owner was there, and it was partly used for some other activity. And this is where we had to have a detailed study to assist the regulator. Next. So when this responsibility was given to it, to our institute, I mean, what we had to do, I mean, we had to first go for a detailed reconnaissance study. I mean, spoke to the Pollution Control Board people about the practice of their waste disposal. I mean, they did not have any concrete idea, because a lot of people who were involved earlier, they were retired. And some indication was given to us about the locations of these waste disposal ponds. Then we had to go for a detailed hydrogeological and hydrochemical study, set up a network of observation wells, when established the topographic, direction and the probable groundwater flow direction. And then to get a feel of where exactly the solar evaporation ponds are located, we had to go for a detailed geophysical study to identify the waste disposal sites. And because that was the culprit, they were generating, I mean, huge amounts of H acid and this mother liquor, and it was being disposed of unscientifically, because at that point of time, there was no proper safeguards. And after this delineation of the contaminated zones, we have to provide an action plan for remediation. Next. So this is the colored water that you see here. These are from the drinking water sources, basically. I mean, these wells are used for agriculture. You can see here that there is this water which looks like Coca-Cola, and then you have this agricultural land behind it also. And this contaminated water is also used for agriculture. I mean, that is for growing paddy. Next. So we had set up something like more than 25 observation wells after establishing the groundwater flow direction. And we could see that this red color, I mean, that is this color value. I mean, it was very high in as many as 5 sources, and slightly moderate away from it. And we could see that this has spread to something like more than 400 meters from the site. And we had detailed discussions with those government department and the well owners. And we got the well details also, because this colored water was coming, and we did not have any knowledge about the screen where that was put in that drinking water source, rather this agricultural well. So based on this blank pipe and the slotting, we could see that the water is coming from the deeper aquifer, and deeper aquifer up to 300 feet, that is 100 meters, is almost contaminated. So this disposal of this mother liquor, that is more than 70,000 to 80,000 mg per liter, that has contaminated the deeper aquifer extending up to 300 feet. Next. So this is the site where our team did ERT survey, because this mother liquor is very conductive. I mean, having 70,000 to 80,000 mg per liter. And so that will have a distinct contrast with respect to the background. That is why I had to go for this ERT survey. And here within that site, we also wanted to have the aquifer property to get the potential of this aquifer. So a pumping test was carried out. Next. So this is the site that is spread over something like 4 acres of land. You can see this white square, and there is another the dark square, and another, this is this copper sulfate square. So the white and the dark, these are basically the probable locations of the solar evaporation pond, because we did not have the latest map of that study area, and whatever was submitted, and it was not a georeferenced site map also. And some indications were given by those villagers that these were the sites, and we could get some idea from the Pollution Control Board people also. So we had all these ERT profiles to see, I mean, what is the extent of this solar evaporation pond, and is there any signature of the solar evaporation on the ERT profiles. And this, I mean, region covered, I mean, marked by this copper sulfate collar. This was basically site of this hazardous waste storage tank, because they had to put lot of this iron sludge and gypsum sludge here in this copper sulfate square. Next. So what we had to do, we did all these ERT profiles, and if you can see it here, this very low resistivity anomalies, that is from something like 4 ohm meter to something like, I mean, 13, 14 ohm meter. I mean, this is the region which was almost overlapping with that region which was earlier identified as the solar evaporation pond. And that solar evaporation pond, as we could gather from the Pollution Control Board officer, it was to be some 2 to 3 meter deep. But when we could we could take a look at the profile, the low resistivity anomaly was extending up to something like 15 meter. And this position of this low resistivity anomaly, it was conspicuous in all the profiles. And based on this zone from the different profiles, we could identify that solar evaporation point. I mean, the 2 solar evaporation points, and also the hazardous waste disposal site. But only for information, I am including one particular image because of other restrictions. Next. So once this extensive ERT campaign was completed and we could identify the potential this solar evaporation ponds, I mean the 2 solar evaporation ponds, then we had to go for a targeted soil sampling by engaging one driller. And here you can see, I mean, we had 3 meter deep trenches, and you see this black zone basically, and the fluid that was coming out had something like that 70,000 to 80,000 mg per liter. I mean, that was characteristic of this mother liquor. So we at first this systematic ERT, we delineated these solar evaporation ponds. Then we had a targeted sampling where we could confirm the presence of this mother liquor. Next. So this is the site, this delineation of contaminated area. I mean, this zone, you can see that is, and you can see the site also. And this contaminated groundwater has spread something up to mg5 and beyond that. And the soil is contaminated within this site, that is this, I mean, yellow polygon. So based on this soil contaminated region and the groundwater contaminated region, we have prepared an action plan, and wherein we have suggested that the soil that is contaminated has to be transported to the TSDF site, the treatment, storage and disposal site, I mean, where it has to be treated and stabilized. And the groundwater, which is mostly due to the organics, it has to be treated through a pump and treat method. I mean, a mix of activated alumina, or I mean, it can be ozonation and EV filter. And for that, we are already working out. We are in touch with the Pollution Control Board. So the final message is, I mean, this problem is huge, basically. This contamination from H acid, it is there in the Gujarat state also, in Padra, that is some 40-50 kilometers from Baroda. And this is a huge problem because the contamination is also very old, and it is going on for the last so many years in Padra also, and now it is going to be handled in Punjab. And such pollution cases are going to come up in future also if it is not properly addressed. But at the same time, these are opportunities also. I mean, this is where probably all our people like hydrogeologists, geologists, geophysicists, groundwater modelers, and environmental engineers can work together. Next. So this is the final takeaway, that geophysics will play a big role in site remediation, because when remediation is in progress, and we would like to see the performance of remediation, that is also the stage where geophysics will contribute meaningfully. And the time has come to work together with chemists, hydrogeologists, modelers, and environmental engineers. And the role of geophysicists will be enhanced with the new notification of Central Pollution Control Board in 2025. I mean, if you look at the latest notification of Central Pollution Control Board, as many as 120 sites in the country have been declared as contaminated sites. 120. And all these sites have to be remediated. And if remediation has to take place, then the characterization, the site delineation has to be done by geologists, hydrogeologists, and geophysicists. No other discipline can give a better image of the contaminated region at the resolution that our geophysics people can give. So it's a great opportunity for geophysical community, and we need to have some kind of improvisation of the tools also. It is not just the remediation, because remediation will be left to the chemists and the environmental engineers. But in future, the performance of remediation at the field scale has to be done by geophysicists. And there are tools like spectral induced polarization and other tools also, which are also being used. In Indo-Italian project, we did try, and we had limited success at the laboratory level. But we had a long way to go, basically. And probably this is the time when academics, research institutes, and industries and private consultants can work together. I mean, that ecosystem has to be built up, and probably with Dr. Rana, probably we can have such opportunities to work in future. Thank you. Okay. Yes, please.
So much, Dr. Pujari, for such an interesting presentation. And
Thank you, sir.
I'm sure participants must have got benefited by your detailed insight because you have been working in this field. And as you very correctly said, no discipline lives in isolation. We have to
Exactly.
work with chemists, hydrogeologists, geologists, other experts in the field. Because as we are conducting this webinar, I got a number of questions. And the best part is that the nature of question remains the same. Means I've got them directly on the chat, so it's not in the chat here.
Yeah.
And to the people who have sent this question, I like to reiterate which I said that when we are talking of role of geophysics, we are not saying that geophysics lives in isolation. We are
Exactly.
also not undermining the importance of sampling and laboratory testing, etc., etc. In any discipline of geophysics for near surface application, we always say that it basically can help you optimize your effort and fill in the gaps which you have between your discrete information. Geophysics is giving you a picture of a much larger area, giving the lateral and the depth extent of the entire area. And then whatever discrete points you have, once you put that data along with your geophysical data, you have a holistic image of the entire thing. None of the two live in isolation, they complement each other. There
Yeah.
are people who also say that we are doing this to validate geophysical results. That is not the approach. There is nothing like validation of each other results. Remember where both the sciences are fitting in. Geophysics for a quick study of the entire area, giving the lateral and the vertical extent of whatever contaminants are. You cannot have a chemical analysis of your contaminant based on geophysics. It is working on the principle of physics. So the only thing you will have is, let's say, resistivity. All right. Now, if you want to go for the analysis of that, you need samples of these places, right? The amount of contamination will affect the resistivity in some way, and then do that correlation, do
Yeah.
that calibration, and that's the way to go forward in this. Okay. So thank this thing your presentation. Now I'll take few of the questions which are there. And Pragya ji has been very kind enough to put the questions in my chat box. I'll first take the questions from the chat, then I'll come to hand raised, and I'll give the opportunity for you to ask the question directly. First question was about GPR. It said, how do you detect the horizons from GPR result, etc., and how reliable it is? Okay. First of all, in GPR, what we are measuring is two-way travel time. We are not measuring depth, right? Two-way travel time is being converted to depth. Conversion of two-way travel time to depth is dependent on the understanding of the velocity in the medium in which the electromagnetic waves are traveling. More accurately you are able to determine this velocity, more accurate your depth will be. There are various ways of determining this velocity. I'll not go into that, but it starts from hyperbolic reflections, matching, right, going from common midpoint GPR surveys, goes to calibration from some ground truthing which is available, etc., etc. There are so many ways of doing that. How accurately you do that? Unfortunately, that's a problem. Many GPR practitioners are using GPR in the factory set mode. Factory set mode gives a depth time to depth conversion based on a assumed RDP of, let's say, 5 or 9. Equipment is delivered to them, and on one scale they see time, on the other scale they see depth, and they think that that's end of it. That's not end of it. That's the start of a disaster actually. Okay, you cannot use factory settings. You have to determine the permittivity in every campaign and then use that to change your time to depth. That's the mandatory part of it, and it is so important that the permittivity which you measure in the evening can be so different from what you measure in the morning. just because it rained in the evening, suddenly the RDP will change of the ground. So it's so important to do it at the time when you're doing your observation. So it will be as accurate as you're able to do this conversion of time to depth. Then second question was, can we comment on the type of contaminant getting infused? Say for a landfill, there is possibility of multiple contaminants. Can we differentiate between their spread using ERT? Again, how much confidence? All right. So as I think I already answered this question. What you're measuring is one physical parameter, and that is resistivity. How resistivity is getting affected by different contaminants cannot be determined by ERI alone. If you have only one type of contaminant which increases the resistivity, then based on lowest resistivity to higher resistivity, you can say highest level of contaminant to lower level of contaminant. But that's all. It's a only qualitative interpretation you can do. Type of contaminant and all that. No, you have to go for real test, taking out the sample, doing the laboratory testing of these samples, and that's where you can do the correlation. Then next question was, how can we determine fractures in bedrock through ERT? Was shown in one of the slides. What is secondary porosity? So when we are talking of things like rocks and then fractures in the rocks, that is what we call secondary porosity. All right, it is not the porosity which is like primary porosity which you have in something like sandstone. Okay, it is a secondary porosity which has been created because of breaking of the mass. So when you have rock and these fractures are there and fractures are filled by any conductive medium, it can be even water, or in this particular case, it was slime. You will have a resistivity which is much lower than the rock resistivity itself. That is how we are differentiating in that. Next question was, in refraction seismic tomography, the seismic waves are generated by hammering. How deep can we do, etc., etc. Generally, hammering. If you're doing hammering for seismic refraction, your depth of investigation is limited to 25, 30, 35 meters. It also depends on the medium. Loose soil will have much lesser depth of investigation. Good competent soil will have more depth of investigation, but 25, 30, 35 meters is the max. If you want to go deeper, you have to go for example, things like weight drop. If you want to go even further deeper, you have to go for explosives. All right. So, but hammer, since your question was up to hammer, 25, 30 meters is almost the limit of hammer based seismic refraction tomography. All right. So, these were the questions I had here, and I'll request team to please give me questions if there are any else. Pragya ji, especially, please give me in the chat if there are any further question. Now we'll go to raised hand. Mr. Amrit Lal Haldar, you can please unmute yourself and ask your question, please.
Thank you, Dr. Anna and Dr. Pujari. It is a very insightful and thoughtful lecture. The first lecture I heard, and second time I could get the chance. I had a question for both of you, sir. Dr. Anna, you have mentioned very good work you have done, of course, that specific and site-specific things you might have analysis also. But I'm very much impressed that especially the subsurface contamination. But my specific question is that for arsenic, for the heavy metal, arsenic lead, sir, can we detect specifically that this is arsenic contamination and this is lead contamination, especially in UP, you might be knowing, especially in eastern UP, Gorakhpur and other thing near that Ghagra, they are very much, enriched in the arsenic. Similarly, for in West Bengal also, and of course in Lucknow also it is there nowadays, that arsenic contamination. So my specific question is that, can you detect that what kind of heavy metal is there and what is the depth, or is there any depth limitation? So this is the first question, sir. Let me hear from you.
Dr. Pujari, would you like to take it?
In fact, the thing is, arsenic, the way it is found in the subsurface, so getting it linked to the resistivity signature, I think probably it's not feasible. But one thing that I can tell, Dr. Rana, you might have heard about Dr. Parasnis, not DS Parasnis, who is a book we used to read. Hello?
Yeah, right.
Yeah. I think he had done some basic work only using this resistivity for arsenic, but I never came across that work in any research paper or anything.
All right. So,
Yes, sir.
Haldar Saab, I'll
Sir.
give you a general question to your specific answer, which I have been trying to give from the starting of the webinar. Okay. We are measuring certain physical properties. Okay. In this case, let's say we are talking of resistivity.
Yes, sir.
Resistivity can change because of so many factors. All right.
Yeah.
Now, all the interpretation is based on your background knowledge of that particular area. Okay. And ultimately, if you have to link to a particular contaminant, right, you have to do the calibration of this resistivity data with the sampling data for sure. Okay. Without that, you cannot do any interpretation in terms of chemical composition, because geophysics is not geochemistry. Here we are measuring a physical property, right? Any chemical interpretation can be drawn based on correlation with the chemical sampling of the data. Okay. That is the basic message which I would like to give to all the participants who have similar questions. Okay.
Any depth of limit, I mean, depth of penetration limitation is there for the 2D, I mean, this resistivity mapping 2D or 3D?
Well, to be very honest, 2D resistivity I have done up to a depth of 500 meters. That's the max I have done. Okay. The commercial equipment which are available today are, let's say, 120 electrodes, 10 meter spacing, 1200 meters spread. So 400 meters, 350 meters has become pretty standard for depth of investigation these days. But remember, as you go deeper and deeper, your resolution keeps suffering. Okay. So there
Yeah.
is a relationship in that. But otherwise, depth of investigation is not such a major issue. And if you go for 2D kind of a thing, I have conducted 1 kilometer deep soundings in Afghanistan, in Jaisalmer, in Jodhpur, and Barmer for River Saraswati project. Afghanistan for giving them water in Herat region. 1000 meters, that is 1 kilometer deep soundings I have conducted there. And even deeper soundings have been reported from other parts of the world, but that's my personal experience. Yeah. Not so much of a limitation.
Thank you. Thank you, sir. Now,
Thank, yeah.
another question is that to Dr. Pujari. Dr.
Please.
Pujari, you have given a lot of reference for EIA, Environmental Impact Assessment, especially for the notification, say 1996, 2006.
Yeah.
But I know very well, of course, I got chance to be there in SIA, SIAC, and your NIRI members are also there. Occasionally they used to participate. But in industrial land, as you
Yeah.
were mentioning that site remediation, the industrial, especially for the sugar industry, though they are telling the zero discharge, then how come that iron is leaching there, say especially in groundwater? So it is very, very dominant, especially the within the periphery of say 10 kilometer or say 15 or 20 kilometer, that in the river, that in the especially for the downside, that iron downside, but of course not I am telling about the surface water, but in groundwater in that area, irons are depositing. So in the EI notifications also, it should be incorporated, sir, and the site remediation, it should also be incorporated. Because I am seeing last 4 years I was there in UP, in SIA, SAC, and again I got the second team member in this September. So because you have mentioned a lot of things regarding the EI, that's why I'm asking.
No, the
Yes,
thing
sir,
is, see, I mean, in our setup, I mean, first of all, I mean, one thing is that, I mean, whosoever applies for EIA in our country, there have been very few cases wherein the EC is refused. That is number. Now coming to this compliance, I mean, there is often non-compliance, I will say. And that creates all the problem. That is why NGT is there, basically.
Yeah, right. But
and see, I mean, in our situation, I mean, it is really difficult, I will tell you. I mean, people want, I mean, when this pollution was there in Tamil Nadu, it was a big problem. Everybody agreed. And the problem was so severe that our court had to, I mean, ban all the tanneries in the country. You see, I mean, how much people suffered in that process. But that time, I mean, NEERI and CLRI came together and gave some technology. See, I mean, the thing is that it is everybody's problem basically. And
Sir,
I mean, all have to work together, then only, I mean, there can be some solution. I mean,
So we are
working in isolation will not lead to any solution.
correct. So
you're
now,
right, sir.
Haldar Sahab, now we'll take few more questions, Haldar Sahab,
Okay,
please, with your
please.
permission.
Okay,
Yeah,
sir.
it's
Thank
a
you.
very interesting discussion. I don't want to let it go, but I think we'll do justice with few more.
No problem,
Uh,
sir. No problem.
yeah.
Please, please.
So
Thank you.
Mr. Ayaz Mahmood Dar has asked a question which is related to integration of various tools, etc. And that's about integration data of data sets, and that's a theoretical question. I will reply to you one to one because that's not related to this particular webinar. His one question is, I would like to hear about time lapse 4D, which was mentioned, and its real time possibility. So yeah, this is a very good thing. So when we talk about time lapse ERI or anything, let's say you are trying to see the movement of a contaminant plume over time, right? So what you do is you just do not take one time measurement, but you take repeat measurements, and then you are able to visualize how the changes are happening in the value of resistivity with time. And that is what we call time lapse resistivity. And you are adding a fourth dimension of time in like X, Y, Z, and then time dimension. That's why it becomes 4D. I hope it answers your question. Then Mr. Abhinandan Prasad the Barnwal has asked, what software can we use to create tomography of ground using cross-hole sonic logging devices? I'm asking this as most of the software and devices are designed to work for a cylindrical pile. Uh, I don't know if I understand your question well, but there are number of software which are used between any two faces. These two faces can be two boreholes, they can be actually two sides of the dam, they can be two sides of a wall, and they can be top and bottom of a stone slab. So there is nothing like pile. There are different software, they come from different manufacturers. Like practically anyone who is making the tomographic devices like geotomography, or there are other companies, geo device, all of them have their respective software also. If you need any particular further information on that, please get in touch with me. I'll tell you what all software I'm using. Then Mr. Rabindra is asking, how can I determine the concentration of crude oil in water for possible quantification in the description of the absorption kinetics? Crude oil in water. Dr. Pujari, would you like to take this?
Crude oil in water.
Yeah. For possible quantification, the description of absorption kinetics. Mr. Rabindra, are you there? Can you come online and just unmute yourself and explain your question further?
There is, I can, if the question is shared, I can discuss with our chemistry person, the water
Sure.
chemistry person.
I will send
yeah,
it to you. Right.
because we have an NABL lab also here.
Okay. Then Mr. Santosh Raj is saying, can we determine the depth of borehole which is already drilled with geophysical investigation? We do it all the time when we do well logging. So in
Yeah.
well logging, we always find the depth of the borehole, and we always have problem with the driller. He always says I had drilled 20-meter extra, and our logger is going up to 20 meters less than that. But that's a simple sounding you can do with a dead sonde also. So Mr. Santosh Raj, are you there? You can ask your question, Mr. Santosh Raj. Are you there? I don't understand your question because otherwise it's very simple. You do the simple sounding using a dead sonde, and you can find depth of the borehole. Okay. Now, Mr. Anand Kumar Parida is saying, can resistivity increase with some kind of filling or only decrease, like you said, in case of water? Increase or decrease completely depends on the host and the target. All right. So there is no such rule that resistivity will only decrease or increase. But when we are talking of contamination, we are generally talking of more content which will make flow of electricity easier. So it is generally seen in the decreasing side. But that's why whenever you are interpreting your results, you need to be very sure about what are you looking at and what are you can say the target and host characteristics. What is the contrasting physical properties? Mr. Ghan Bahadur Shrestha is asking, Dr. Pujari, do you record IP? What is the role of IP in detecting pollution? Dr. Pujari, this is for you.
Yes, in fact, when we have used only spectral IP measurements for organic pollutants at the lab scale, not in this inorganic contamination. At the lab scale, we had got some success. Yeah, but IP data collection, I mean, itself, it's very cumbersome. That is what we have seen at the field scale.
Next question is by Mr. Ayaz Mahmood Dar. Can we differentiate clay lens and contamination plumes using ERT? That's a very good question.
Yeah,
And if you want to differentiate clay lens, best is to include IP with
IP, yeah.
ERT,
Yeah.
because in IP we are measuring chargeability, and in clay you have a different chargeability values than what you will have in saturated or contaminated plumes. So once you add IP with your resistivity, you are able to solve this problem. So that is why we generally recommend doing IP and ERI together, so that we can differentiate these low resistivity zones, whether they are because of high salinity of water in this particular zone, or they are because of presence of clay lenses. Mr. Dar, I hope I answered your question. All right. So I think we have answered all the questions in the chat box. If there is any other question, you can raise the hand, although we have really gone long in this particular webinar. Uh, but it's interesting. So if you want, if you have any question, you can raise your hand. Is there any raised hand here? I don't see anything. Santosh Raj again, what type of sounding technique is used and how to interpret the data for borehole depth identification in alluvial areas? Mr. Santosh Raj, I requested you to come online if you are there, and let's speak. Because when it comes to borehole depth identification, as I said, you lower something in the borehole and it sits at the bottom, and that's how you find the borehole depth. We do it by well logging. When we are doing well logging, our logging tool sits at the bottom. It need not be a logging tool. It can be a dead sonde also. So yeah, that's what it is. All right.
Hi, sir. It's Santosh.
Yeah, Mr. Santosh, what exactly is
Yes.
your question?
Actually, can we able to identify the casing depth which has been given from our client side, and the data which has been observed during our video logging of the borehole? Because those depth has been actually it is silted from the material. We have to make sure that how much siltation has been taken place, and what was the uh, depth of the casing which has been placed there, actually placed.
Well logging is basically giving you depth of whatever you want to see. You want to see casing or naked borehole and all that. But if the borehole has been silted from the bottom and your sonde cannot go beyond that, unfortunately, at least I'm not aware of any way of finding out how much siltation has happened, and because you're not going able to go there, and just slim and just too deep. So, Dr. Pujari, is there anything you can suggest on that?
Yeah, what you're saying is correct.
So that's if the
Yeah,
borehole has been silted from the bottom, unfortunately, either you punish the driller or you take his word for it, whatever he has drilled. Okay. So, all right.
because in
And
that case,
Okay,
probably
okay,
you
sir,
may not
thank
be, I mean, you may not be knowing basically. I mean, you are at the mercy of the driller.
exactly.
Because it happened once in Nagpur during the Sekifer mapping. I mean, they were not, it was basically, they got into some kind of surprise. I mean, The driller drilled and it was left like that, but the well collapsed and they could not even verify, I mean, what was the depth.
Correct. We have Dr. Narendra Pal Singh here. Singh sir, please ask your question.
Good afternoon, Sanjay Ranaji and Bharat Pujari. Thank you very much for your wonderful presentations. I'm from ONGC. And my question is not directly related with the contamination or its monitoring. My question is slightly different that how can we use geophysical methods in detecting the buried channel of Saraswati River that has been, vanished for almost 5,000 years ago. And as a part of ONGC, we were given this project to, find out the buried paleo channels of Saraswati. So which of the tools that Sanjay Ranaji has discussed can be rather more effective in locating paleo channels of Saraswati River?
So since we are talking of very deep paleo channel here, it's not very shallow. One other tool which is very useful, of course, remains electrical resistivity method, which can really give a good idea of the paleo channels. It is being used for various works. Then if you want to cover large areas, you can also have time domain electromagnetic, which can be done even in the aerial mode. You can do helibone time domain electromagnetic, which again is giving you a good conductivity profile. And since it gives practically 2D or 3D profile of the subsurface, it gives you a much better idea of your paleo channels, because the network becomes much easier to understand when you're seeing it in 2D or 3D instead of seeing in 1D. Because I'm aware of the Saraswati project which ONGC took up, and that time, at least when I remember, it must have been 12, 14 years back. Only vertical electric soundings were done there, followed by some drill holes. Vertical electric soundings are giving 1D data, very discrete data, right? So unless you take it into 2D or 3D, it becomes very difficult to understand the entire network. So you have techniques like, helibone or airborne methods, time domain electromagnetic, even ground-based TEM, then electrical resistivity imaging. So ultimately, electrical based methods are very good for paleochannel studies, have been used world over. And since it is much deeper, I'm not even talking of things like GPR, which is okay for shallower part of it. Hope that answers your question.
If you allow me, I want to add his question, Dr. Pal. Dr. Pal, you might be knowing this satellite remote sensing, that if you map the hydrogeomorphological mapping, you'll get the precise paleo channels are there. And for the depth of investigation for 3D, then you have to use this geophysical perspective.
That is the right sequence. As I always say in my other presentations, when we start working on any area, it starts right from satellite images, remote sensing, geological maps, then goes to geophysics, then goes to drilling. We are messing it up actually at that step only. We directly jump for drilling without doing geophysics in most of the projects. So that's a big problem we have. Thank you for your contribution. All right. So I think with this, we'll come. We have few more questions, is it? How can we GPR? Sorry, I'll just take these last questions, right? Okay. What about gas soil contamination, Mr. Manisha? Then what is the way to evaluate the migration of contaminant? Right. So whichever contamination we are talking about, there is no simple answer to this is the right method. It completely depends on the host property. You have to study what is the host property, what is the target property, and based on the contrast between the two, you have to choose the right method. That's number one. Number one, please avoid doing anything using just a single method. Always try to use combination of methods, because two very different formations can have one physical property which is the same. So you always try to use combination of methods to come to a unique solution. Migration of contaminants. The next question is about migration. Whenever we are talking of migration, movement, time related activity, that is where we have to go for something which is done repeatedly. So you do an observation today, you do observation sometime later, and then you are able to see the changes, and that's how you can see the migration. GPR interpretation, gas contamination, again the same thing. Can GPR interpret gas contamination? Depends on what is the depth of investigation you are having. Gas, always changes the dielectric properties of the soil. So when we talk about leakage from the gas pipelines, GPR is one of the tool which is used very frequently. Wherever gas is leaking from the pipeline, it changes the dielectric properties drastically. GPR done with the pipeline detects it beautifully. If you are asking that, yes, it's a great tool. Otherwise, number of parameters to be looked upon. So whenever you have a question, can we use this method or what method can we use for this problem? Remember, people like me and Dr. Pujari are always there available without absolutely any commercial obligation. You please feel free to write to us. My email ID I'm putting in the chat box right now. Whatever question you have in your mind, whatever problem you are having in mind related to subsurface, please feel free to write to us and we will get back to you. If we have the answer, we'll give it right away. Even if we don't have the answer, we'll find out from our network of geophysicists and friends and try to get an answer to you. Like Dr. Pujari just said in response to one question, he will talk to his people in his chemistry lab. We are not expert of all the fields. We just know geophysics, and that too may be part of it, right? So we'll definitely come back to answer whatever it is. Last question we'll take from Mr. Sandeep. I'm working on Mumbai Metro project. It's shallow buried tunnel at some location. Tunneling is complete, facing more collapses there. We have completed. We have to check the pockets from the ground to the entire alignment so that in future no settlement observed. Yeah, so along the metro corridor, there are many geophysical tools which you can use. You can use the ERI, MASW, SRT, seismic tomography. If your tunnel is completely going under buildings and you can't do anything on top of it. So, Mr. Sandeep, my mail is right above your message. Please use it to send this question to me and whatever is the problem, and we are sure we will be able to come up with solution. Yeah, I'm suggesting combination of tools. I never suggest one single tool. You said which tool you suggest, not a single tool. Combination of tool depending on the site condition. So there cannot be a direct answer to any question unless we understand the site condition. All right. So with this, I think it is time to thank Dr. Paras Ranjan Pujari for joining in this webinar. And thanks to all the participants for being with us. And recording of this webinar also will be made available for those who could not join here. And even on those who have joined, go ahead and enjoy the recording again. And may I request everyone to please come on screen. Rashikji, it is possible to put all the participants on screen, and I'll request you to open your cameras so we can take a group photograph. Is everyone on his? Yeah, that's much better. So yes, I can see many smiling faces. Good thing is, even after almost 2 hours of webinar, most of the faces are smiling. So we have not done a bad job, it means. All right. So who is taking group photographs? Rashikji, are you doing it?
Yeah, I am also
Yes, sir.
taking photographs.
Anushka, you are there? Wonderful. Okay. Great, great, great. So thank you very much.
Okay, thank you, Dr. Rana, and thanks to all the participants. It was a great experience.
Thank you so much. Thank
Always,
you, everyone.
it's always pleasure to be associated with the Aqua Foundation.
Same here, Dr. Pujari. Thank you
Yeah.
so much.
Okay, thank you.
Thank you, sir.